During another presentation, audience members are asked to draw a card from a standard 52 card deck. Observe the card, then put it back. If all 30 audience members draw a card, what is the probability that only 2 aces are seen by the audience? What is the expected number of aces seen by the audience? So we have each person drawing a card and then putting it back. That means the probability that each individual person sees an ace is not influenced by the people around them, or the people before them, or after them, for that matter. So that means that the probabilities are all independent. Oops. Let's change that to black. It's the same probability every single time, and we're doing 30 different times, or 30 different trials. So those, when I hear those together, I think binomial. Specifically, there are 30 different trials, and we're saying the probability of a success, well, I guess I should probably define what a success is here. We're counting the number of aces that are seen by the audience, so I'm going to count a success as drawing an ace. Alright, the probability of drawing an ace out of a deck of cards is going to be 4 out of 52, or I could reduce that down to 1 out of 13. And we're saying, what's the probability that only 2 aces are seen by the audience? And this is exactly 2 aces. It doesn't say at least or at most or anything like that. So I'm going to say x is exactly equal to 2. So this is a pretty straightforward binomial. PDF. N is 30, P is 1/13, and X is 2. So I'll pull out my calculator. Alright, let's turn it on. Let's see, I want to go binomial PDF, so that's going to be in distributions area. Down to binomial. And I know it's a PDF, not a CDF. Again, because this is, the PDF is the probability of getting exactly 2 in this case. If I did a binomial CDF with the 2 there, that would be getting the probability of getting at most 2. So if I said the probability of getting at most 2 aces by the audience, that would be a binomial CDF. If there was a probability of at least 2, I'd have to do some sort of, that's a 13. I'd have to do some sort of complement and then probably use my binomial PDF, or CDF, most likely. Alright, so 30, comma, 1/13, comma, 2. That gives us 0.2737. Alright, for the second part here, what is the expected number of aces seen by the audience? Now, in general, the expected value, we would want to do 0 times the probability of getting 0 aces, plus 1 times the probability of getting 1 ace, plus 2 times the probability of getting 2 aces. And conceivably, this could happen all 30 times. 30 times the probability of 30 aces. But of course, this is a lot of work. I don't want to do it that way. So let's think about what other options we have. Well, this is binomial. And we know that when we have a binomial experiment, we can find the expected value just by taking n times p. So in this case, we take 30 times 1/13, 30/13, which gives us 2.307, whatever. I'll call it 2.3 aces. So you would expect, on average, if you were to repeat this trial again and again, on average, you would get 2.3 aces from the audience. How does this change if the audience members held on to their cards instead of putting them back? Well, since they were putting them back before, I said that these were independent. The probability that one person gets an ace is not impacted by the probability the second person gets an ace. So if you said that they're putting the cards, or they're keeping the cards instead of putting them back, these are no longer independent, and we're now saying this is without replacement. We're just counting how many aces are drawn there. So I'm going to say there's no sort of order. It doesn't matter if the first person gets the ace or if the fourth person gets the ace. If they get an ace, that's all that matters. So order doesn't matter. So these two taken together mean we're talking about combinations. And you'll notice I'm talking about combinations. This is a counting technique. This is not something directly used for probability. Instead, to find the probability, I'm going to have to use the probability of E equals n of E over n of S. This is how I'm going to make it into a probability. I'm going to figure out the number of ways that we could get a certain number of aces divided by the number of ways that we could draw those cards in total. So this would then become, well, the probability of getting 2 aces, because that's the first part of the question. That was this part over here. The probability of getting exactly 2 aces, well, there's 4 aces in the deck, and we're talking about drawing 2. So from the 4 ace cards, we're drawing 2. From the 48 non-ace cards, there should be 28 cards drawn. This is exactly the same as if I was saying I'm drawing 30 cards. What's the probability I get exactly 2 aces out of those 30 cards? Just a hand of 30 cards. So divided by 52, choose 5. And I can figure out what that is. 4 choose 2 is 6. 48 choose 28. I have no idea what that is. That's going to be some big number. Oops. Divide that by 52, choose 30. I wrote 5 here. That's not right. This should be 30. I was talking about drawing a card, or drawing a hand of cards. Obviously, I was thinking of a poker hand there when I wrote 52 choose 5, because that's the denominator we had for all of those poker card problems. All right, we get a 37.312. It's actually not all that incredibly different, a 27% or a 37% chance. We're a little bit more likely to get 2 aces if people are not drawing, or not putting them back. You know, you've already drawn over half of the deck at this point. All right, if you're trying to figure out the expected value here, though, for the expected, there is no shortcut for the expected value when we're talking about these counting techniques. Instead, we'd have to figure out, okay, what's the probability? I'm going to write up my full distribution here. So 0, 1, 2, 3, 4. The numbers of aces that we could draw, if we're drawing 30 cards, would be 0 through 4. We'd have to figure out the probability of 0, which is going to be, what is that, 4 choose 0, 48 choose 30, over 52 choose 30. All of these are going to be over 52 choose 30, so I'm just going to kind of put those on at the end. This is 4 choose 1 times 48 choose 29. This is 4 choose 2 times 48 choose, no, not divided by, choose 28. That's the one we just figured out up there. This one is 4 choose 3 times 48 choose 27. And this one is 4 choose 4 times 48 choose 26. And these are all going to be the same thing over the same thing. So let's figure out these numbers. I'm just going to figure out the numerator, because if I take 0 times this number, add it to 1 times this number, so 0 probability of 0, plus 1 probability of 1, plus 2 probability of 2, plus 3 probability of 3, plus 4 probability of 4. That part goes away. Now that whole thing I don't care about. 1 times the probability of 1, this is 4 times, well, that's some number. I'm probably just going to have to plug this stuff into the calculator. 48 choose 29, there's no simplifying that I can see. That's easy. This is going to be 2 times 6 times this this thing right here, 48 choose 28. Trying to just reduce the amount of keystrokes I have, so anything that I can do fairly easily, I'm doing. 3 times 4 choose 3 is 4, so this is 12 times the probability, or rather, not probability, this is 48 choose 27. plus 4 times 1 times 48, choose 26. So I'm able to do this, at least the numerator part, with just 4 different calls to the combination function. We get 4 times 48, choose 29, plus 12 times 48, choose 28, plus 12 times 48, choose, let me scoot this over so I can see what I choose 27, plus 4 times 48, choose 26. That's my numerator. And I'm going to divide that by 52, choose 30. Which is 2.307. 6.243 is 10 to the 14th over 52, choose 30, which is approximately 2.307. If you were to have this process repeated multiple times, you would get, on average, 2.307. That would be your expected number of aces that came up. Let's compare this to up here. This is 2.3. Actually, let's do a little bit more accuracy. 2.307. You look like those numbers are actually quite similar. This is not because I was able to use the binomial probability, but there's something else going on here. So we don't need to know exactly what's going on there. I'm just gonna leave it at the fact that if you're trying to figure out an expected value for a binomial distribution, you can do this shortcut. For other distributions, you generally can't do that shortcut, although there's obviously something going on here.